There's a cooling trick you can use right now, and it will cost you absolutely nothing. It has the potential to lower the temperature of your home by up to 6 degrees Fahrenheit, and it requires no electricity, no machinery, and no work of any kind. This principle is called cross-ventilation, and it's a method that builders in the Middle East, West Africa, Southeast Asia, and the American South were all using long before the electrical grid ever existed. The principle is simple, yet effective. Hundreds of years ago, ancient civilizations across desert, jungle, and coastal climates recognized that if you could move air through a building, you could make it survivable. One of the most sophisticated early examples comes from the hot, arid cities of present-day Iran. By at least the 14th century, builders there were constructing towers called badgers. These tower-like structures rose above the roofline and were designed specifically to catch wind at altitude, where it moves faster and more consistently than at ground level. When the wind blew, the tower acted as a pressure-driven intake, channeling air down into the rooms below. In the cities of Yazd and Kashan, buildings designed around this system have been in continuous use for over 600 years. On the other side of the world, builders in Borneo and Vietnam arrived at a different but equally effective solution. In the humid tropics, the problem is not dry heat but stagnant moisture. Their solution was the longhouse, a dwelling raised on stilts above the damp ground, wide open and plain with no internal walls to interrupt the passage of air. In West Africa, the Taguna used aligned doorways and large shaded openings to create a permanent cross breeze through the interior. Then, when West Africans arrived in the Americas, this architectural knowledge came with them. The result was the shotgun house, which became the dominant residential form of the 19th century American South. A shotgun house places every room in a single file with the front and back doors aligned in a direct line. When both doors are open, the house becomes a wind tunnel, allowing for undisturbed airflow through the building. The dog trot house carried the principle further still. 2 separate living units were connected by a central open-air passage under a shared roof. That passage was shaded and open at both ends, which made it permanently the coolest zone in the building. Because it was the lowest pressure point in the structure, it continuously drew air out of the rooms on either side, providing a natural exhaust that made the adjacent spaces habitable without any mechanical cooling systems. The physics behind all of these designs was formalized by a Swiss mathematician named Daniel Bernoulli in 1738. His observation was this: as a fluid moves faster, its pressure drops. And in a building, that relationship has a direct architectural consequence. Wind traveling at altitude moves faster than wind near the ground, which is slowed by trees, terrain, and surrounding structures. Faster air means lower pressure. A window or vent placed high in a wall or in a roof monitor above the main roof line sits in that lower pressure zone. The air inside the building is pulled toward it, creating a natural exhaust path even without any mechanical assistance. The pressure difference between the windward and leeward faces of a building is what drives the airflow through its interior. Research has found that when openings occupy between 15 and 20% of the wall area, the wind speed passing through them can be up to 18% higher than the local outdoor wind speed. The building acts as a funnel, compressing airflow through restricted openings and accelerating it in the process. If the openings become too large, exceeding roughly 60% of the wall area, that pressure differential collapses, and the ventilation becomes turbulent and disorganized. On windless days, the mechanism shifts to what engineers call the stack effect. Warm air is less dense than cool air and rises. In a building with openings at different heights, that density difference creates a vertical pressure gradient. Cool, dense air enters through the lower openings and pushes warmer indoor air out through the upper ones. The taller the building and the greater the temperature difference between inside and outside, the stronger that pull becomes. Architects amplify the stack effect using solar chimneys, vertical shafts exposed to direct sunlight, often painted black or fitted with south-facing glass. The air inside heats well above ambient temperature, creating an updraft that pulls fresh air through the building, even on still days. We can all use this knowledge of cross-ventilation to regulate the temperature of our homes, but numerous variables determine how well any individual building will ventilate. Rooms that are shallow between exterior walls allow air to pass through them without losing momentum. The types of windows play a big role here too. A casement window, for example, that opens fully and swings outward acts as a physical scoop, redirecting its prevailing breeze into the room rather than simply letting it pass by. The building orientation also plays a huge role. A house with its longest wall perpendicular to the prevailing summer wind captures the maximum pressure differential across its facade before a single window is opened. Now, opening a couple of windows in your house might sound a little basic, but there's real data to back up how well the principles of a cross-ventilation system perform in real-world situations. In Mumbai, India, researchers studied the Kanchenjunga apartments, a high-rise design by architect Charles Correa, which incorporated deep garden terraces on every floor to function as wind scoops. The The study found that cross-ventilation reduced operative temperature by up to 9.5 degrees Fahrenheit on typical days and by 11.5 degrees on the hottest days of the year. The number of hours in which occupants experienced thermal discomfort dropped by 58%. And in Seville, Spain, one of the hottest cities in continental Europe, researchers monitored a historic building through a full summer by coordinating the operation of windows and courtyards in a deliberate sequence. The building maintained an average indoor temperature 5.4 degrees Fahrenheit below the outdoor peak, with a measured cooling efficiency of 40%. Here, occupant comfort hours improved by 30%. So the effectiveness of a cross-ventilation system has been proven, especially in lower humidity climates. Yet, despite this performance record, American homes have spent the last 70 years moving in exactly the opposite direction. As mechanical cooling spread through American homes, architects began removing the architectural features that natural ventilation had depended on. High ceilings, which allowed heat to rise above the level of the occupants, were lowered to 8 feet to reduce the volume of air that the HVAC unit had to condition. Front porches, which had provided shaded transition zones between inside and outside, were eliminated in favor of the ranch house and the picture window. These large, fixed panes of glass admitted solar heat directly into the interior and created a greenhouse effect that increased the mechanical cooling load they were supposed to be supplementing. By the late 1960s, air conditioning had become a standard feature in the majority of new American homes, and building design began to reflect this shift. The modern building code then reinforced this trajectory from the regulatory side. The International Energy Conservation Code now mandates continuous air barriers designed to prevent uncontrolled air movement. The logic behind this is that a sealed building retains conditioned air and reduces the workload on the mechanical system. However, at the same time, by sealing the building against uncontrolled infiltration, these codes also sealed it against intentional natural ventilation. For the HVAC industry, this regulatory framework became a commercial goldmine. In 2025, the Environmental Protection Agency mandated the phase-out of R410A refrigerant, requiring its replacement with lower emission alternatives at a cost increase of approximately 20% per unit. Rather than prompting a reconsideration of mechanical dependency, this transition reinforced the message that climate control is a problem to be solved with increasingly expensive machines rather than natural solutions. There's a straightforward economic reason behind the floor plans themselves. Cross-ventilation works best in shallow buildings, 1 to 2 rooms deep between exterior walls, or arranged in L-shaped or U-shaped footprints, so that every room has at least 2 exterior exposures. These forms are more expensive to build. A 2,000 square foot single-story ranch home, which is easy to naturally ventilate, can cost 10 to 20% more to construct than a comparable 2-story home because of its larger foundation and roof area. Despite this, the knowledge of cross-ventilation is powerful, and it is there for anyone to take advantage of. As we already discussed, the most impactful decisions for natural ventilation are made before construction begins. Building orientation is the first variable. Research the prevailing summer winds in your area before finalizing a site plan. The United States Climate Consultant Database, which is freely available online, provides prevailing wind data by region for every month of the year. Orienting the house so its longest wall is roughly perpendicular to those summer winds determines the pressure differential across the facade before a single window is specified. Window type determines how much of that potential is actually captured. Casement windows are the most effective type for natural ventilation, or a louvered or jalousie window with its adjustable horizontal blades allows air through nearly its entire opening and can direct that air upward, downward, or straight across the room depending on the angle of the blades. For existing homes, the most effective single investment is a whole house fan. These are mounted in the ceiling of a central hallway and draw air through every open window in the house while exhausting it through the attic vents above. A properly sized whole house fan can reduce indoor temperatures by 4 to 6 degrees Fahrenheit in under an hour. Installed costs range from $800 to $2,500, and operating costs are a fraction of a central air conditioning unit running the same duration. But for those not looking to undertake any construction, the principles that govern the shotgun house and the Badger can still be applied to almost any existing floor plan with nothing more than an understanding of how air moves through a room. The first thing to understand is that cross-ventilation requires a minimum of 2 openings, one for air to enter and one for it to leave. In a room with a single window, that window's effectiveness is limited to whatever air can enter and exit through the same opening. But opening a door on the opposite side of the room changes that dynamic entirely. The moment air has a clear path from one side of the room to the other, it moves with purpose rather than pooling. The distance between those 2 openings matters as much as their existence. Research suggests that cross-ventilation functions effectively in spaces up to 40 feet wide, but the shorter that distance, the faster and more consistent the airflow across the occupants inside. If a room feels stuffy despite open windows, the problem is often that the distance is too great, or the path between the openings is interrupted by furniture or a partial wall. Repositioning a sofa or a bookcase can change the airflow dynamics of a room in a way that costs nothing. The size relationship between the inlet and outlet openings also changes the quality of airflow inside the room. A smaller opening on the windward side and a larger one on the leeward side increase the velocity of air passing through the interior. The air is compressed as it enters through the smaller gap and released into the room at a higher speed. That increased velocity is what produces the cooling sensation against the skin that makes a breeze feel several degrees cooler than the air temperature alone would suggest. In hot and humid climates, this sequence requires adjustment. Outdoor air admitted during humid evenings can raise interior moisture levels enough to offset the temperature benefit. In the American Southeast, night flushing is most effective on evenings when outdoor humidity is lower and works best when paired with interior dehumidification rather than used as a standalone strategy. Cross-ventilation is an approach built on the ancient principle that a building that moves air through it will always be cooler than one that does not, reducing interior air temperatures without turning on a single mechanical system. A lot of what this channel covers was nearly lost, not because it stopped working, but because the industry moved on to something more profitable. The truth is, cross-ventilation provides a viable, cost-effective way to keep indoor spaces cooler, especially during the summer months when mechanical cooling can become prohibitively expensive. By simply understanding how air moves through a room and making a few adjustments to your home, you can dramatically improve indoor comfort without the need for costly air conditioning systems. What's more, using natural ventilation methods like these is a form of passive cooling that not only lowers energy bills, but also reduces your overall carbon footprint. This is an opportunity to not only save money, but also contribute positively to the environment. The techniques of cross-ventilation, when understood and applied correctly, give us a powerful tool to combat heat and humidity, providing a more comfortable, sustainable way to regulate indoor temperatures. As more homeowners and builders turn to these traditional methods, it's clear that the solution to cooling our homes doesn't always have to rely on expensive and energy-hungry machinery. Sometimes the answers are simpler and more in tune with the natural world around us. It's a reminder that while technology has its place, there are ancient practices, rooted in natural understanding, that can help us live better, smarter, and more efficiently. By applying these principles, whether by adjusting window types, orienting your house correctly, or even installing something as simple as a whole house fan, you can begin to benefit from a cooler, more energy-efficient living space. The knowledge of cross-ventilation is there, available to anyone who's ready to embrace it. And with today's rising energy costs, taking advantage of natural cooling methods is more important than ever. Now, if you want to learn how one wall, built from the right materials and oriented correctly, can store enough heat from